So, we will discuss some more tests about uh, the convergence and the divergence of the series, which is going to determine the convergence and divergence of the series. So, let us look at this one. So, suppose we had been given with certain a n's which are, let us say, decreasing sequence, and a n's are greater or equal to 0. Now, let us try to look at. So, we have a 1 is somewhere here, a 2 is here, a 3 is here, a 4 is here, something, it is a decreasing, non-negative decreasing sequence. Now, we are adding the values of this. Definitely, this is going to be, now if I look at the area of this joining them, area of this function region under the curve, this is going to dominate just the point values of this a n if it is a continuous function intuitively. So, that is what we call is the integral test. Let f be a continuous positive decreasing function on 1 infinity, such that f of n is equal to a n, or rather assume let f of n is equal to a n. So, what we can say is that summation over a n is convergent if and only if improper integral integral 1 to infinity f of x dx is convergent. Recall that what is the meaning of the improper integral to exist or is convergent? We need to look at 1 to x, this integral is Riemann integrable for every x greater than 1, then we take the limit as x goes to infinity. If that limit exists and finite, then we say that the improper integral is convergent. So, we will not prove this, intuitively this is what is the proof. So, let us apply this result to determine the convergence of certain series. Recall that we have considered this series n equal to 1 to infinity. What we know earlier, p lesser equal to 1 divergent series, series diverges, p greater or equal to 2 less than infinity convergent, by comparing it with 1 by n square and they are comparing. So, we left it open for the case 1 less than p. So, now a n, consider the function f from 1 infinity to r given by f of x is equal to 1 by x to the power p. Now, in this domain, this is a continuous function and this is a decreasing function. Therefore, it satisfies the condition of the given statement and f of n, this is equal to 1 by n to the power p. So, now summation the series 1 by n to the power p converges or diverges simultaneously if integral 1 to infinity f of x exists or not in the improper sense. Let us now try to do this. We have done it earlier, do it again. So, we need to check whether integral converges or not. Okay. In order to do that, what we need to do is that 1 to x dt by t to the power p, this must be Riemann integrable and this is Riemann integrable. Let us find what is the integral. Integral will be x to the power minus p plus 1 divided by minus p plus 1 minus 1 by minus p plus 1. If p is not equal to 1, because if p equal to 1, then we know that this is ln x. So, now this is going to be 1 by 1 minus of p if I take common, x to the power 1 minus of p minus of 1. In order to check that this is improper integral exists, we have to take limit x goes to infinity. Now, limit x goes to infinity of 1 by 1 minus of p into x to the power 1 minus of p minus of 1. This is going to be a finite limit, finite if p is greater than 1. If p is less than 1, certainly this is not going to be a finite limit. So, for p greater than 1, definitely this is going to be a finite limit. So, we conclude by the theorem 1 by n to the power p n equal to 1 to infinity is convergent if and only if p is less than infinity, p is greater than 1. So, this in fact tells us that why this series 1 by n to the power p series is convergent or divergent. Okay. So, sometimes here we know that we are assuming most of the times our ANs are non-negative number, then many of the tests holds true. Suppose for example, for the ratio test and in the root test, because we are taking the nth root of a number, we are forced to consider ANs to be non-negative. Now, in the ratio test we may not, what we need only is that AN is not equal to 0. So, then if we have a sequence, let us say AN, then in the ratio test we find that AN plus 1 mod AN, this limit goes to L and L is less than 1. So, what do we get? Then this will imply that summation over mod of AN is convergent. So, can we conclude AN convergent? As a matter of fact, this is true. However, the converse may not be true. What we have seen is that AN may converge, but mod of a n may not converge. We will again come back to that little later. Given that mod of a n converges, then what we need to get is that we need to look at S n. S n is nothing but, now if you look at S n minus of S m, then this is going to be summation over n equal to n plus 1. Let us say m is bigger than or m plus 1. If I assume n is bigger than m, then this is m plus 1 to n of a n. Now, if I take the mod, then this is lesser equal to summation over n equal to m plus 1 to n mod of a n. Now, as mod of a n is a convergent series, therefore, if I look at the partial sum of the mod of S n, this is the partial sum related to mod a n S n minus of the partial mth partial sum of mod of a n. We know that this is a convergent sequence, in particular this is Cauchy. So, this will go to 0. Therefore, what we get is that S n is Cauchy, is a Cauchy sequence, and we have stated that every Cauchy sequence in R converges. So, this will imply that S n converges. So, that will tell us that if mod of a n is convergent, then a n convergent. This suggests us to define something called a absolute convergence. So, absolute convergence, a series is said to be absolutely convergent series, absolute convergent series, a series let us say a n, if summation over mod of a n converges. We will see that there will be some series which may converge, but may not converge absolutely. So, obviously, if a n consists of non-negative numbers, then there is no distinction between the absolute convergence and the convergence, because mod of a n is going to be a n. So, as we have seen in the ratio test, if we determine of the limit of mod of a n plus 1 by mod of a n, then we can conclude about the convergence of the series. Now, when we are talking about the series which does not have the same sign, that is where the absolute convergence is coming into picture. For example, what we have seen is that n equal to 1 to infinity minus 1 to the power n plus 1 by n, or in general one can look at this series minus of 1 a n. So, now this series oscillates with some terms are positive, some terms are negative, again positive, negative alternatingly this is happening, alternating series. Now, how to determine whether this series converges or not? Now, let us look at so here a n's let me take to be non-negative number, it's let's just take positive for our benefit. So, we need to determine S n, right. So, what happens, suppose this is A 1, then this is nothing but also equal to S 1. Now, in addition, if I assume that A n is greater or equal to A n plus 1, that is a decreasing sequence. So, now decreasing means S 2, if I want to write, this is going to be A 1 minus of A 2. A 2 is a smaller number than A 1, because we are assuming that A n's are decreasing. Therefore, for S2 I have come here up to A1. Now, for S2 what do I need to do? I have to subtract something A2, this one is A2, and what do I get? This is A1 minus of A2, this is my S2. Now, what is our S3? So, S3 means we need to add A3 and A3 is less than A2. So, we add up to this S2. So, this is A3. So, we get it here as S3. Now, for S4 we need to subtract A4, this is A4. So, what we get over here is S4, right. So, similarly what we will find that S6 here, S5, S6, S7 is going to be here, S8 is going to be there. So, here what we are finding that S2, S4, S6, S8 they are increasing and S1, S3, S5, S7 they are decreasing, and this is S2, S4 they are everything is bounded above by S1 and nothing can go below S2. So, this is something like a monotonic sequence. So, that is what essentially is what we are going to write down. This is Leibniz test. This test about the alternating series. Alternating series, what does it say? Let A n non-negative and be a decreasing series, decreasing sequence with limit of A n goes to infinity is equal to 0. Then summation over minus of 1 n plus 1 A n equal to 1 to infinity converges. So, before proving this, let us see some example of this. So, if you grant me this result, then first let us look at the example summation over n equal to 1 to infinity minus 1 to the power n plus 1 by n. Here 1 by n is greater than 0 and 1 by n plus 1 is less than 1 by n. So, decreasing and 1 by n this goes to 0. Therefore, by Leibniz test, this says that this is convergent. Now, any alternating series we should not kind of apply it blindly to, because they are alternating in sign. So, we should apply the Leibniz test. That is not true, because what we need to understand that there are two conditions. One is that A n decreasing and the second condition limit of A n goes to 0. If these two conditions are satisfied, then only we can say that this Leibniz test is applicable. So, for example, if we do something, if we had been given with n plus 1 by 3 n plus 4 n minus of 1, then this, as you can see, that A n this converges to 3 by 4. So, we cannot apply this test. However, in another example 3, let us look at minus of 1 to the power n plus 1, then n square by n cube plus 1. Now, obviously, they are what A n this goes to 0 and A n's are positive. This is very easy, because n's are positive. Now, we need to test that they are decreasing, then only we can apply Leibniz test. So, how do I show that they are decreasing? The very easy way is that you look at f of x equal to x square by x cube plus 1. Now, you look at f prime of x, this is going to be x cube plus 1 square, then this is 2x into x cube plus 1 minus of x square into 3x square. This is equal to 2x to the power 4 plus 2x minus 3x to the power 4 by x cube plus 1 whole square. This is equal to 2x minus x to the power 4 by x cube plus 1 square. Now, decreasing, if f is a decreasing function, then obviously f of n equal to n square by n cube plus 1 is going to be a decreasing function. So, now if the derivative is negative, then we are done. That means what we are looking at, 2x is less than x to the power 4. This is if and only if 2 is less than x 3, if and only if 2 is 2 to the power 1 by 3 is less than x. In particular, if x is greater than 2, then obviously this is a decreasing sequence. So, we are interested in this. So, therefore, this is decreasing. So, a n decreasing. Hence, what we can say that by Leibniz test, this is a convergent series. For the Leibniz test, what we need to check is that this decreases to 0. Okay, so, let us end this lecture by giving the proof of the Leibniz test. So, now you consider S of 2n. As we have seen, S of 2n is lesser equal to S 2n plus 2, S 2, S 4, right, S 6. So, this is an increasing sequence. So, now if you define something like let us say T n is equal to S 2 n, then this T n is an increasing sequence and S 2 n is lesser equal to S 1 for all n. So, now T n is an increasing sequence which is bounded above. Therefore, by monotonically increasing sequence which is bounded above must have a limit. So, limit of n goes to infinity of S 2 n is equal to, let us say, S prime. Similarly, if you define something like Z n to be S 2 n plus 1, what we have seen is that Z n is a decreasing sequence and bounded below by S 2. Thus, again this is a decreasing sequence bounded below, and monotonic decreasing sequence which are bounded below will have a limit. So, let limit n goes to infinity S 2 n plus 1, this is equal to S double prime. So, now you have a even partial sum which converges to S prime and the odd partial sum which converges to S double prime. If we can show that S prime is equal to S double prime, then we are done, right. And remember that here in this proof we have not used that a n goes to 0. So, now let us look at S double prime minus of S prime. This is equal to nothing but limit, by limit laws, n goes to infinity S 2 n plus 1 minus of S 2 n. Now, S 2 n plus 1th partial sum minus nth partial sum. So, this is equal to limit n goes to infinity A 2 n plus 1. So, this is given to us that this is going to be 0. Therefore, so S prime is equal to S double prime. Hence, limit of S n, n equal goes to infinity is equal to S prime. Therefore, the series is a convergent series. Okay. So, there is a very interesting another test which I will not give you the proof, but which is very useful for certain particular kind of series, that is called Cauchy condensation test. So, this says that if a n greater or equal to 0 and a n is decreasing, a n plus 1 is lesser equal to a n, this is decreasing for all n, then summation over a n converges if and only if summation over 2 to the power k a 2 to the power k converges. This is the subsequence of a n 2 to the power k. So, we look at this with a factor of 2 to the power k a to the power k, if that converges. So, I will just give an example. So, let us look at summation over 1 by n log n square. So, whether this is going to be a convergent series or a divergent series. So, as you can do the comparison. So, now what you want to do is that you consider 2 to the power k, then divided by 2 to the power k, and log n is log 2 to the power k square, which is equal to, or rather first let us try to do it with just with the 1 by n log n. So, then this is 2 to the power k, 2 to the power k goes away. So, this is k. So, this is a divergent series. Therefore, this series is divergent. What about this square? So, if I take this square, then this is going to be k square log 2 square. Now, this is the convergent sequence. So, when we are doing 1 by n into log n to the power p, so this becomes very handy to test with the Cauchy condensation test. I am not giving you the proof of this. If need arise, then you can use this powerful test to determine whether your series converges or not. So, to kind of wind it up, so you have the most fundamental series is the geometric series. Then you always try, if you look at the proof, that we have used several times that our knowledge of the geometric series, whether by comparing it with the comparison test, with the root test, with the ratio test. So, then you have the comparison test, ratio test, and the root test, and the integral test. And then the series which has alternating sign varies with the plus minus plus minus plus minus. In those cases, we have got Leibniz test and then this Cauchy condensation test. So, essentially what we need to see is that this comparison test is one of the very powerful, and in all the proof of the ratio test or root test, you are using this comparison test. So, thank you.